I'm Claire. So today let's solve if we have this sort of recurrence and we're gonna find the general form of it. So actually we have this form, so that's a(n plus 2 equals p(a)n plus 1 then time plus q(a)n. Now the question is that a(n plus 2 equal to 5(a)n plus 1 then minus 6(a)n. So we're going to find a general formula, and actually we are talking about this problem. Actually it has something about the general series, so general difference series. So first let's solve the problem. We can actually move this part over here. So we have a(n plus 2 minus 5(a)n plus 1 plus 6(a)n. Okay, right? Okay. What's the next step now here? Okay, we're going to equal to 0. Now, we're going to set that a(n) is equal to r to the n. So r is some value we're going to calculate it out. So calculated r. Now we're going to calculate r. So r to the n plus 2 minus 5 r to the n plus 1 plus 6 r to the n go to 0. So we can just factor out the r to the n. So we have r to the 2 minus bracket, of course bracket over here, r squared minus 5r plus 6 then times r to the n. Okay, that's equal to 0. But if r to the n equals 0, that means the whole series equal to 0, right? That's no meaning. Okay, so we're gonna let r squared minus 5r plus 6 equal to 0. Okay, we let this equal to 0, of course, so that's r minus 2 times r minus 3. Okay, that's equal to 0, so r equals 2, r also equal to 3. That's it. So we can just, now actually, I'm going to tell you this is r1, this is r2. So the root of a(n), answer of a(n), we can write that c1 times r1 to the n plus c2 times r2 to the n. Here's another condition, of course. Here the condition is a1 equal to -1 and a2 is equal to 2. Okay, so we have this actually, no, that's equal to c1 times 2 to the n plus c2 times 3 to the n. Okay, now it's the next step. Actually, we're just going to calculate because a1 is equal to, we just plug it inside, so we have c1 times 2 and then plus c2 times 3. Okay, and that's equal to -1. So we have c1 and c2, these two values. We're gonna actually coefficients. We're gonna calculate it out. So now we can think about it's a variable, and we're gonna calculate it out because we have two equations over here. So a2 we have c1 times, actually it's 4 because it's 2 squared, right? So that's 4 and plus c2 times, what's that? That's 9. Okay, then that's equal to, what is that equal to? Okay, so that's 2. Now these two, we can just look. We can both times 2 this equation, so we can both then use this equation to minus this equation, right? Because since 1 has been cancelled out, so that we can find out c2. But this time 2, so c2 times 6, and in here -2, so this minus this is 4, and then here it is c2 9, and so here that's 3. 4 over 3. So plugging over here, that's 4, and then 4, so I'm going to move it over here, that's negative 5, and so that's negative 5 over 2. Plug it back inside, so we have an equal to, now okay, so 2 cancel out, 3 can cancel out, so we have, now because this is negative, so we'll move that term, so that's 4 times 3 to the n minus 1, and then minus 5 times 2 to the n minus 1. Okay, that's it. This, we have to find out our answer. So a1 is equal to, an is equal to this one. Okay, so now we're going to find out y's and how we're going to use this. But first, let's think. We can think that this, so first let's move it here. an plus 2 minus 5an plus 1 and plus 6an. What's that actually? We can write it as an operator times an. So this operator, we can call that L, uppercase L, so L times an. Okay, so that's equal to 1, right? So of course we know L is over here. Okay, so actually, why can an have 2 roots over here? If an has 2 roots, it actually means L has to be linear. L is actually a linear operator. So I can prove it. It's very easy. First, that's L of an, so L times an, so that's L times C1 times 2 to the n plus C2 times 3 to the n. Okay, now let's say equal to, plug it over here, which is we can plug it over here, and C1 times 2 to the n. Okay, so what's that? And we're plugging over here, so, okay. This part is C1 times 2 to the n, so here's 2 to the n plus 2, and here's 3 to the n plus 2. Okay, then minus 5 times over here. This part is n plus 2, this part is n, here's n plus 1 to the n plus 1. Okay, here, just to the n to the n. Now we can just break to 2 parts, and 5 multiple inside just times to this and times to this, 6 multiple same. That means we can break it into 2 parts. First part, C1 times 2 to the n plus 2 minus 5 C1 times 2 to the n plus 1. And then plus 6 C1 times 2 to the n. Okay. Then we're going to just plus C2 times 3 to the n plus 2 minus 5 C1 times 2 to the n plus 1. Oh, sorry, no. This is 3. Okay, this is 3. Then plus 6 C2 times 3 to the n. Okay, this is it. Now we'll prove it because these 2 parts, that's equal to L times C1 times 2 to the n plus L times C1 times C2 times 3 to the n. Okay, this is it. We actually proved that L is a linear operator. So actually there exists a S. So what is S? We'll write it as over here is R, but actually it's S. What's S? The definition of S is S times A, and S is our show operator. So S times A, and we actually have n plus 1. Now, if we have this, now what's the next step? Actually, if we have this, that means we can actually change R to S. Be careful, now note that S is an operator. Okay, so in this step, actually that's R, but we should have written it as S2 minus 5S plus 6. Great. Now then times an. That's it. And that's equal to 0. Actually, of course, I'm going to add that this part, it is lambda. So L equal to lambda. It's no meaningful. We just write it as lambda. We don't need this over here. Okay. So, but S is an operator. We couldn't do this because S is an operator, of course, in this step. See, S is an operator. Over here, we're going to calculate out S. That's no meaning because S is an operator. We have to change it to a value. Okay, so we change it to a value called R. Of course, no, because S times an equal to n plus 1, so an equals S to the n. Now here, we should be writing it as R to the n. Okay, that's it. We can calculate out R. Okay, this is the point, and of course, S is also linear. S is also a linear operator. What is this? Let's think. Of course, so we have S times C1 times 2 to the n plus C2 times 3 to the n. Okay, what's that equal to? That's equal to C1 times 2 to the n plus 1 and plus C2 times 3 to the n. Okay, so that's good. You see this term? Alright, this term, that's S times C1 times 2 to the n plus S times C2 times 3 to the n. Great. This is how we prove that S is a linear operator. Okay. So finishing this, that actually we know. But why an has two parts? Because we had two roots for R, so an has to be two parts because S and L, both of them they're linear. Right? Of course, right here we know actually L is linear, component S is linear, right? S is linear, so L is linear. We can think of that. That's easy, right? Okay. So what's the next step? We actually have we have a different series. So in a different series, we have a difference operator. That's called delta. Okay, so what is delta? Delta is equal to, delta equals what? Delta an is equal to an plus 1 minus n. So the point is, how can we relationship L to L and S? Or something like that. Okay. So an plus 1, that's S. So we'll factor out an S minus 1 bracket times an. Great. Now if we have this, that means S is equal to delta plus 1. So we can use delta. We can substitute delta plus 1 with S over here. But actually, we cannot just plug in to something, a lot of things. And we get, because this part actually that's changed to S minus 2, S minus 3, and that's equal to delta. So we're just putting delta minus 1, delta minus 2. Okay. Times n equal to 1. Oh, sorry, equal to 0. Okay, this is what we can write L as something out of this part. Okay, here actually we prove L as they are a linear operator. So actually, for an over here, because we have two parts, these two parts actually we'll call them, it is a linear combination because L is linear and we just combination these two parts together, so that's a combination. Then L times it, so and then L is linear, so that's what we call linear operator. Linear combination, and there's a linear independent. Independent means there's no relationship each other. Here, this is linear independent because we don't have any relationships for both of them. That is it. Okay, so let's see. what's next step? We can actually imagine because it looks like, where is it? No, not this one. Here, this part. Actually, you can think that this looks like, gonna look at this part. This is where we actually can write it as that C1, R1 times N times, it is 2 to the N times C1 plus 3 to the N times C2, and then minus, actually that's plus, negative 1 multiple of N, and then what you're going to do is to minus 0, then equal 0. That's the point. What equal 0 doing? Of course, you know, because we can think it's in a 3-dimension, and this is the multiple in front. C1 is X. This is the multiple in front of C2 is Y. And this is the multiple in front of A, and that is Z. You see? This, and first, this part, I just write it. That actually means this. Remember, this is the definition of a plane, and this is that. If you go look at a video before that's my video before that, this is a normal vector. These three can create a coordinate, and this is the coordinate of the normal vector, and this is we use the normal vector to do the dot product with P1, right? Okay, so it's 0. Of course, if we calculate out, it's 0. If we find out that's 0, right? We calculate it, we find that's 0, but it actually means, of course, if we just divide the normal vector, the mod of the normal vector, then, so what's that? We just divide this normal vector, and we just divide the mod of it, then we have the least distance from the original point to the plane, and that's uppercase D. So we're gonna divide this, but it's already 0, so we divide this, that's 0. So that means this plane touches the original point. That means maybe we have this. Okay, maybe we can choose a N. Maybe choose a N. So we move over here to the plane. First, the planet can move over here, and even can move it there. But this, so it must touch our normal point. So it's over here. Okay, but N change. Okay, now the plane changes to here. Okay. So, of course, actually, there is another question. I'll add this part later. I told you, because we're gonna give you another question. The question is a n plus 1 equal to 2 a n. So it seems very easy. It's just a geometric sequence, but we can solve it easily. But we can think it this way. So we're gonna move it as a n plus 1 minus 2an equal to 1. Oh, sorry, equal to 0. Okay, so now what is that? Okay, so it's gonna go 0. Alright, so that's equal to 0. Then what is it? 0. So that's r minus 2. And times r to the n, and equal to 0, so r equal to 2, so we have 2 to the n. So So an equal to c1 times 2 to the n. Okay, we don't care about it. The question is this: you don't need to worry about it. What's the an first value? Whatever it is. Okay. Let's think. Just like this. That means up in here, it is in the 2 dimension. Okay, that is a line. So that's an equal to 2 to the n times c1. So this is a multiple of c1, and of course c1 has this, and of course that's y. Alright. So in the 2 dimension, we can think about that. Okay, so first we have choose an n. This is the x-axis, and this is the x-axis, and we choose an n. And then if we choose another n, and another. We can rotate, but we don't know how we rotate it, but just look like this. And so c1 is just the function, the function like a boop. Okay, just like this. Now, actually, we can have a thinking is that if we just move like this, if we just move so this is a race of roots. A race of roots. Now, we can add another race of roots, but the whole thing, maybe we're gonna let the whole thing minus 1. So, the first function over here, we can move that one and start from this point and and rotate. So this is another new race of roots. So this is what we were thinking about. So in the 3 dimension, we can just no more vector in the plan. So we just let the plan. We can just minus not 0, just minus some value, maybe minus 1. So we can just let the plan move to here or somewhere. Okay. Then here, start from here, then move to here, that's here. Okay. And that's like this, then it's like this. Okay. So this, in the 3 dimension, also means we can create a new race of roots. Okay. This is what we can think about in the 3 dimension. Okay. Of course, I just forget to tell you over here. We have some repeat root. These 2 roots, they are the same. Okay, I'm gonna give you a question. The question is, a n plus 2 is equal to. No, let me just write it as this form. N plus 2. Then plus 4a and plus 1, then plus 4a. Okay, we're going to solve, first equal to 0. So we're going to solve this, and then, how can we do this? Of course, the same way, but now you're going to change to r minus, r2 plus 4r plus 4 r to the n. Okay, so that's equal to 0. Over here, that's r. So here's minus. Here's minus. Okay. Now, no, plus. So that's r plus 2 squared. Right. No. It it should be minus. Okay, so r minus 2 squared, so r equal to 2. So r1 and r2 is the same, and so this is a repeat root. But actually, if it's a repeat root, if we just plug it inside, we can just try C1 times n times 2 to the n. Try it, and that's actually also satisfied if we just plug it inside over here. Okay, this is repeated because if you plug it inside, so C1 is, don't think about it, so first, now of course, put an n inside, we have okay, if we just put n inside, we have let's see, that's C1 times n times 2 to the n plus 2, and then minus 5C1 times n 2 to the n plus 1 and plus 60. So let's try it. So C1 we just cancel out. So actually it's sorry, here be n plus 2. N plus 1. So the point is, if we take away the bracket, there's some part is, here's n times and n times. So the n times part, of course, equal to 0 because 2 parts all have n, so of course that's equal to 0. So the part is 2 times here and 1 times here. 1 times here. No. Okay. Okay. And we like this. We just times inside, so this is just minus for just times of 4 inside. Of course. That's right. Okay. There's 2 times inside. It's 4 times inside. I haven't told you why. Actually, that's easy. Because when you change both to 4s to 3 or just k. So r minus k. Then that's minus, over here that's minus, minus 2kr. And here it is k squared. So 2k. Okay, so here's 2k, remember? So if we just put it inside here, it's 2k. And here, still 2. And here, of course, that's k squared. Here's no mind. We don't need to think about this. Okay, so put it over here. I put it inside, so 2 times, that's 2 times k. That part could be 2 times k to the n plus 2. And then minus 2 times k times 2 to the n plus 1. See? This part is there. So actually it's 1. Okay. So, at last, actually, what I'm talking about here, when we create a new race of roots, that's when it is not homogeneous. Let me give you a question if it's not homogeneous. That is, we have a question over here, right? We can just, when it's like this, we're gonna let it equal to 1. So that's an plus 1 minus 2an, and that's equal to 1. Okay, so if we're gonna solve this problem, okay, it's just like what I told you here. Now, first we can think it's equal to 0. We're gonna find a series B. A series B that satisfies Bn plus 1 minus 2Bn equals 0. So Bn is equal to C1 times 2 to the n. What is the next step? We're going to find a series C1. It is a constant series, Cn, it's equal to uppercase A. Now, uppercase A, so uppercase A minus 2 times uppercase A equal to 1. So uppercase A equal to negative 1. Right? Great. So C1 equal to negative 1. So actually, we're going to calculate it out here. Just let B1 plus C1 because she matches. So that's, now we find out An is equal to Bn plus Cn is equal to C1 times 2 to the n minus 1. Because what I said I've already told you here. It's a 3-dimension, no, it's a 2-dimension, so we'll just go down 1. So you erase it. So this is how can we imagine. Okay. Now, let's think something else because this is a discrete because we have r to the n. This is n, and it's a term, so it's discrete. So this is the last part. I'm just gonna told you there's something when it's continuous. So what is it continuous? When it's continuous. Okay, so we have something called d of d times y. So d is an operator. So d is an operator. Okay, now what are we actually going to do? Actually, it is y of x. That I don't write it like this. We can just write like y. And so the way is that y, we said that y is equal to e to the lambda of x. Lambda x. I just write it like this. Actually, just lambda x. Okay, so of course, dy is equal to d over dxy. I'm just derivative. It's just a, well, e to the lambda x. So d times y is equal to lambda e to the lambda x. Okay. Now, if we have this, then what's the next step? I'm going to calculate it out because actually the question is, let me write it, forget it. The question is y prime prime, y double prime minus 5y prime plus 6y equal to 0. Okay. Plug it inside. So d squared minus 5d plus 6 and y. Okay, so it equal to just, you just plug it inside. It's actually, so actually mapping from d and from the continuous and the discrete, d mapping to s. So over here, D gonna change to, you're gonna change it to lambda, right? And S is gonna change to R. So lambda mapping to R. C. Okay, so here we're gonna change to lambda, right? So lambda squared minus 5 lambda plus 6 y. So lambda equal to 2, lambda equal to 3. Okay. Now if we equal to these two guys, so A, not A, whatever it is, y, C1 times e to the 2x plus C2 times e to the 3x. Okay, so imagine we have e to the 2x times C1 plus e to the 3x times C2 plus negative 1 times y equal to 0. Sorry. Minus 0 equal 0. Multiple of C1x, multiple of C2y, multiple of z. Okay, now same thinking with 5, just one different. Because over here it is all vectors for, because e to the 2x is all the values of x-axis, and e to the 3x is all the values from the y-axis. Then so there's, and z is always, so the coordinate of z is always negative 1. So it's on the z equal to negative 1 plan. Every vector we have this, every coordinate is included from this normal vector. Okay, so every of them we have it. So this plan just rotate. We have all of the sort of them. If we rotate from the original point, right? So this is, of course, this is in the 3 dimension of, and that is, it's continuous. So the only difference is discrete, that's n. And so mapping to here, that's x. And n, that's why it's this discrete, right? That's why this is, that's why this is, we can write that so that this okay, and so another one that's yes. Okay, so x is continuous. That's why. That's the difference of both of them. That makes one vector is just first right there, and we just jump to there and jump to there, so boop, boop, boop. And so just rotating. But this one is all of them. And over there, over here, over there, over here. So all of them we have it. Right? Okay. So this is how can we find the general form. We have these sort of recurrence. Also, we've also find that we can, of course, I just tell you, this is what we called first order homogeneous. This is homogeneous, and this is also homogeneous. So this is first order homogeneous, and this is second order homogeneous, because second order homogeneous we have n plus 2 and n plus 1 term, and here we only have n plus 1 term. No, Question, where's the question? Oh yeah, sorry. No. Here, it's over here. The question mark over here, just like these. We have a and plus 1. Okay. We have a and plus 1 and an a. So this is what we're going to talk about today.